When a mass is hung from a spring and mass is set in motion, the object's position oscillates, but those oscillations decrease. This is typically called a damped oscillation. Now let's assume that S of t gives the damped oscillation of some mass, and it's 15 sine of t over e to the t, and this measures displacement from equilibrium. So S is going to be measured in inches and t is in seconds. Let's see if we can see what's going on with the graph. So if we take a little look at the plot, we can see that, remember that this is the plot of the function. At first it goes far away, then it goes back towards its origin, and it eventually rests back at its equilibrium. Let's go ahead and see what the derivative tells us about this mass that's in motion. So let's calculate S prime of t, or ds dt. Let's switch notations here. So this is going to be a quotient rule. So that's the numerator times, the denominator times the derivative of the numerator, which is 15 sine t, minus 15 sine t times the derivative of the denominator, all over the denominator squared. So this should be a pretty quick calculation. We have e to the t, the derivative of 15 sine t is 15 cosine t, minus 15 sine t, and the derivative of e to the t is just e to the t, all over e to the t squared. We can factor out 15 e to the t, just to see if we can simplify a little bit, times cosine of t minus sine of t, all over e to the t squared. Cancel out one of the e to the t's here, so a little bit more simplified. We have 15 cosine of t minus sine of t over e to the t. Now, this derivative is going to give us the instantaneous velocity of this mass at any time t, measured in inches per second. For example, if we wanted to calculate S prime of 2, we would plug in 2 for t, so we'd have cosine of 2 minus sine of 2 over e to the 2, which is approximately negative 2.69, and again the units on that is going to be inches per second. And what that tells us is at 2 seconds exactly, the mass is moving downwards at an instantaneous rate of 2.69 inches per second. Downwards because of the negative. If we had calculated a time and it come out positive, it would be moving back upwards towards its equilibrium spot, which is what we were seeing in the graph earlier. In fact, we can verify this on our graph. So right here is 2. We can see that our object is going downwards at that point. And if we wanted to, we could verify this. We could calculate our derivative at 2. And there's our negative 2.069 inches per second.